This is Yutong Hao. I'm a junior mechanical engineering student from Penn State. Today I'm here to present my IE 312 final project on 3D printing of reinforced polymers. First, let's look at our current 3D printing materials. Here listed the common 3D printing materials that we are currently using. ABS and PLA are the most popular 3D printing materials. They both are thermoplastics. PLA is stronger and stiffer than ABS, but poor heat resistance. ABS is weaker and less rigid, but also tougher and lighter. All of the materials are low cost, except for PVA. PVA is a perfect support material because it is a water-soluble synthetic polymer. The PVA filament dissolves in water. On the other hand, let's look at our reinforced polymers. Among the choices, fiberglass, carbon fiber, and Kevlar are the three most popular reinforced polymers. They can be applied broadly into our conventional 3D printing materials using different volume fractions. Now the question is, how do we combine our reinforcement materials with our conventional polymer? Through two materials extrusion methods, the fiber-reinforced polymer composites could be printed. The first one is a fused filament fabrication, or FFF. It's used for continuous fiber. In this method, we could use traditional polymers such as PLA, ABS, and nylon as a matrix, carbon, glass, and Kevlar fibers as a reinforcement. The processing of continuous fiber can be done by simply modifying the print head. Different approaches to print continuous fiber have been demonstrated in Figure A above, such as 1. The situ fusion of thermoplastic liquid resin before extrusion, or the second approach, in situ fusion of molten thermoplastic with fiber as nozzle, or 3. Extrusion of pre-impregnated fibers. When printing continuous fiber reinforcement polymer through the first approach, which is in situ fusion of thermoplastic liquid resin, glass fibers pass through the solution containing dissolved ABS. It's observed that the viscosity could affect both resin content and traction force to put the fibers within resin. And 2. Fibers are fused into molten plastics filament at the nozzle. The fibers are extruded automatically without any feeding device, as they tend to drawn into the nozzle by the movement of melted thermoplastic. And finally, for extrusion of pre-impregnated fibers, continuous fiber bundles are pre-impregnated with thermoplastics, such as nylon and alum, and then directly extrude from the nozzle. And as to print these continuous fibers, we could use a method as liquid deposition modeling, which is LDM. It's used for discontinuous fibers. In this method, thermoplastics such as PLA resins have been used as a matrix material. So far, the reinforcement exists only in form of discontinuous fibers like silicon carbide viscose, carbon fibers, glass fibers, and CNT. Reinforcement materials are mixed homogeneously with liquid resin to form paste-like composite feedstock. As mentioned, to print the reinforced polymer composites, there are two methods, the short fiber method and the continuous fiber method. Now let's take a look at the advantages and disadvantages of the two production methods. First, let's talk about advantages of the continuous fiber method. For carbon fiber reinforcement, there are several advantages. like high stiffness, low elongation, ability to withstand high temperature, low specific gravity, high tensile stress, low weight, low thermal expansion, chemical resistivity. Those characteristics help the carbon reinforcement finding its application in the field of engineering. In aerospace and nuclear engineering, military, civil engineering, and motorsports are some popular areas where carbon fibers are widely used. Now, in some cases, those can replace standard materials that have previously been used. For instance, aluminum was replaced by carbon fiber reinforcement polymer in aerospace applications because of its excellent properties. In terms of the short fiber method, which is a consistent mixture of the two materials, it is high quality composite part. It has high flexural strength and is also easy to produce. As I mentioned, short fiber reinforced polymer composites are relatively easier to be produced by FFF, as they are extruded in normal filament without the need for extra fiber laying mechanism. FFF, however, suffers from limitations like porosity and voids. Voids have been observed to form in between the extruded filaments, thus leading to delamination and reduced tensile strength. Reinforcement is also more effective along the direction to the filament as compared to the across the layer direction, as fibers tend to lie along the extrusion direction, resulting in high anisotropy in mechanical properties. Now, why to investment in fiber reinforced 3D printing materials? Let's look at the continuous fiber printing first. The results from the tensile test on specimens printed by the Mark I printer is shown in the first three figures above. We can see from the four samples, they have an average strength and stiffness of 986 megapascal and 62.5 gigapascal respectively. And the results from the short carbon fiber nylon filaments, showing they have a lower tensile stress and flexural stress, as well as the shear strain. The advantages of reinforced polymer in 3D printing are due to their excellent mechanical properties, such as high stiffness, low elongation, high tensile stress, low weight, and low thermal expansion. Also, they're easy to customize and meet specific needs. For example, in the field of biomedical engineering, we can customize by the patient's needs. Also, it's a big save on tooling, modeling, and tooling cost. Also, it can reduce the labor cost. Let's look at the limitations of the reinforced polymers. For carbon fiber, there is a decrease in toughness, yield strength, and ductility, an increase of porosity with increased level of carbon fiber. And for the glass fiber, the flexibility and handleability, existence of voids leading to 20 to 30% loss in mechanical performance. In this slide, we'll talk about the cost. The effect of fiber orientation to tensile properties versus cost is shown in the figure. The group of isotropic reinforcement materials shows the best ultimate tensile stress, with a mean about 350 megapascal, of course with the highest price. The group of concentric reinforcement materials exhibits moderate to ultimate tensile stress, with a mean of 150 megapascal and lower price of $15. And the traditional 3D printing polymers shows low overall optimal tensile stress below 50 megapascal, with less than $5 of material cost. The manufacturing process time is expected to be the same, so that with the non-reinforcement polymers, since in both continuous and short fiber methods, only the matrix, which is the base material, is being melted. The same production time won't bring any additional cost to the company. Also, since we will be using the same 3D printing machine, there won't be additional equipment cost as well. In conclusion, the material cost is the biggest part in the whole investing plan. The manufacturing readiness level (MRLS) are used with assessments and are designed to assess the maturity of a given technology system or components from a manufacturing perspective. According to the criteria listed above, I'll give an 8 for the MRLS score of reinforced polymer. Here listed the sources I used. I mainly rely on the first three, which are all research paper or journals, and I believe they provide unbiased opinions. And finally, thank you for watching.